Not the first time.
I should just pause this. I do want to get to this worksheet. I guess before we begin, I just want to show you, see, this part you will have to sketch somewhere, just maybe on a piece of scratch paper, but I want you to see the parent function for rationals. So I'm going to just add a blank page here. So I'll not use graph paper. How's that? So that I can kind of make mine look like yours. That'll be there you go, fair's fair. So most of us don't just have graph paper laying around. So if you just have a piece of notebook paper or nice. Yep.
Just take a sec. It's very rude. I'll take a sec.
So not really like a formal definition or anything, but get used to this now because this is what we'll do for at least a few days. These are rational functions, and what we need to understand is that just because you see a fraction doesn't make something a rational function, okay? There are lots of functions that have fractions that are not rational. They're polynomial functions, but to be a rational function, you have to have a variable in the denominator. And very neat things happen with rational functions. And so I wanted to show you just the parent function and then some little tweaks that we can do. It'll make the lesson-y part a little bit slicker for us. So if I were just to graph y equals 1 over x, it's going to have a couple of, first off, what we call asymptotes. And I am at an advantage over you here in that I have the ability to make like colored and straight lines, maybe stuff like that. But anyways, and I'll talk about why these go where they go. But this particular function, the parent function, has a vertical asymptote at x equals 0. And it also has a horizontal asymptote at y equals 0. And the behavior of this is it's like anything. Like if I was going to teach you about parabolas, I would just want you to see what all parabolas generally look like. And then we'd start sketching them and moving, bless you, we'd move them around and flip them over and make them fatter and skinnier and stuff like that. Well, a general rational function looks like this. It's asymptotic up here, and then it just kind of cruises its way down like this, and then it's asymptotic down here as well. Now, there's also another side to this. That half of the curve only takes into account x values that are positive. X can also be negative. So when x is negative, then of course the overall fraction takes on a negative value, and this graph behaves exactly the same as his counterpart. I mean, they're both parts of the same graph. They're the different halves of the curve. And he has his asymptotic behavior, but he has his down in quadrant 3. So as far as like rational functions 101, that's what the graph of a rational function could look like. Now, there are many modified versions of this, but this is the one from which they all come. Horizontal asymptote at 0, vertical asymptote at 0, and very predictable behavior. Okay, yeah, ma'am.
So if you don't know if you don't know the value of x, you have to drop both of those since it could be negative or positive.
Yeah, like maybe I'm not making myself clear. This function looks like this. It is both pieces of the graph are the function. So if you think about like if we were to make a table, let me just show you real quick. So like if we made an XY table, if I said like, let's pick some X values and you said like, okay, X is, I don't know, like 2. If you picked X as 2, and then when you put that in place of X and you go 1 over 2, you get a Y value of 1/2. So you can actually see the point like 2, 1/2. Do you see that on the curve? But then if we were to think that the other one is like a different graph, we would be failing to consider that, well, what if X is like -4, right? It's like any other table we've ever made. X can be whatever it wants to be with some exceptions like here. But like if X is -4, what does the whole function value take on? What is it? It'd be just -1 over 4, right? If X becomes 4, then this fraction quite literally is 1 over, or -4, I said. If it's 1 over -4, then the fraction is just -1/4, right?
And then this graph, there's every number has an output except for 0.
Correct. And let's talk about that as soon as I sketch this one. So like if I went to -1, 2, 3, 4, then you can see the point -4, -1/4. So sorry if I said that wrong, but the two arms, the two parts of the graph, they're not separate things. They have to be separated by an asymptote. And that goes back to something Brady started to say. Why is there a vertical asymptote at 0, like this, the vertical line, that top to bottom? Why is he there? Because X can't be 0. And that's really what we primarily are going to study a lot over the next few days, is really what is X not allowed to be? It's this idea of what's in the domain and what's not. X can be anything in this function except 0, because if you put 0 into the machine, what happens? Breaks down. You've known for years that you can't divide by 0. And so that's where a vertical asymptote is going to come from, is the fact that, hey, X tries to get there, but it can't. And when it approaches something that it's not allowed to be, it approaches it, I'm going to say this word for like the 10th time, asymptotically. So it gets closer and it bends as it tries. And then the concept of infinity pops in. And if you wanted to see where the infinity comes from, if you have a calculator, it doesn't matter if you don't, but try putting in like 0.0001. And if you had a calculator, I mean, I have one, I can do it for you if you want. Mine's somewhere. So if I put 0.0001 in place of X, do you want to make a prediction as to what's going to happen to the Y value before you look at it on your calculator? Not quite, but it does get bigger. And that's something that we've learned along the way, and we sometimes have forgotten, is that if you divide by little numbers, answer goes big. Divide by little, answer go big. And so if you take 1 and divide it by a tiny little 0.0001, it's going to come out to 10,000. And so an input of 0.0001 gives an output of 10,000. And that's where you really get to see that asymptotic sort of behavior, is that, I mean, I'm approaching the y-axis from the right side, and that graph is just bending up, and it's already up 10,000 units. Like I couldn't graph it that high if I tried. What happens if we get closer? What if we did 0.000001? It gets bigger and it just keeps trying to get there, but we know that it can't. And this really leads us into a calculus-y sort of concept about limits. About what we're talking about here is what's the limit of the function as X approaches 0 from the right, and what's the limit as X approaches 0 from the left. What happens if we creep up on that from the left side? What if I were to put in something like -0.0001?
It'd be negative.
It's just the -10,000. And that's where you see this downward. If you can see my green pen down here, that's why the asymptotic behavior is heading south, because we're putting in a baby little negative number, giving us back a Mongo negative whole number. So now this is what f of X or Y equals 1 over X looks like. Now there are tweaks that we make to this. I'm going to show you this by just using Desmos just real quick, and then I'll go through the notes officially. And the notes are primarily going to be this, but also just like the problems themselves. So I think this is where Desmos can really, really shine. You never play on Desmos, yeah, you really just should. I mean, so if I did Y equals 1 over X, there is the aforementioned parent function, right? Would anyone like to make a prediction as to what's going to happen if I change the 1 on top into a 2? Yeah, can you be a little bit more specific, maybe? Yeah, it's going to stretch vertically. So like the point like right here, I don't know if you can see where I'm like moving my mouse. That point's going to get pulled higher, right? Because we're multiplying by 2 on top instead of by 1. So like if I do Y equals 2 over X, you see that the graph got stretched away, just like you guys theorized that it would. Okay. And what do you think happens if I put a negative on it? What if I did the 1 over X parent function, but I stuck a negative in the front? It does. It flips quadrants. Good. So right now it's currently up in quadrants 1 and 3. If you slap a negative on it, it just goes zoop, and now it goes up to quadrants 2 and 4. Right. So the negative in front, and I know we've been down this road before, and we will get back to talking about like just the old making a table that you guys seem to like, but it's good going into a graph to just know kind of generally what am I up against? What is its behavior? Where should I expect to see things? So the green one is the one that happens if we put a negative on it. Okay. So you should be comfortable with that. I'm going to delete these now. And let me ask you another question. What do you think is going to happen if I do 1 over x? But after I put like a +3, +3,
Oh,
it's going to move it up 3. And we've learned this before that if it's an afterthought plus or minus, it's a vertical shifter. So that graph, if you watch, if I type in +3, it just went whoop and slid up 3 units. And likewise, of course, if I get rid of that, what would happen if I put like a -4?
Down.
It's going to go down 4. Got it? How do you guys think I could make it move left and right?
Subtract or add from them.
Subtract or add right down inside the argument. Again, you've heard this before. You've heard this song before. If I go down into the argument of x, if I put a +2, where's it going to go?
Left.
Very good. It's going to go left 2. Remember, this is the bass-ackwards one. So if it's 1 over x +2, it actually moves back to the left 2. Right? And same for what if I wanted it to move right, then I would put like a -2. So all those factors come into play. But again, I've learned with you guys that that's not how you like graphing. We're still going to make tables. That seems to be the unanimous selection for how to make good graphs. And I appreciate that. But like I said a minute ago, just knowing what you're up against is a good kind of first step. And then the table will help us to nail down some points. So that's the gist of it. You're going to see other types of functions. You're going to see functions that don't just fall into 4 quadrants. You're going to see functions that fall into 6 spaces. It's going to get a little bit odd, but today is not odd. Today should be, knock on wood, pretty straightforward. So let's get to it. Do some problems together. Page 1. You already kind of have a picture of it in your mind. There are 3 transformations that we can expect to see here. Sorry if it's a little early for this question, but what's one thing that's different between this and the parent function? It's going to move down 1. What else? It's going to move right 1. And what else? That's going to be 4 times stretch here, right? So we can kind of already feel all that happening. Is it going to get the negative quadrant flip? No, so we can expect the bulk of the activity to be happening in our upper right and our lower left in quadrants 1 and 3, right? And if that doesn't happen, then something's gone awry. So the best plan of attack is first off to find the asymptotes. Anyone who teaches this in any school in any part of the world would first tell their students you need to find your asymptotes. So the first thing we want to do is find a vertical asymptote. And our vertical asymptote is going to come from wherever x is not allowed to exist. Do you see any numbers in this? We've been talking about this the last couple of days that x is not allowed to be. X can't be 1. That's an excluded value. Do you see any way on the top of the function for that x minus 1 to ever cancel out? That's a weird question. It's like I caught you off guard there, but no, right? There's not like another x minus 1 up above it that I can cross it off with, right? Therefore, it remains an asymptote. As you'll see in about 10 minutes or so, when the discontinuity can be removed by crossing it, canceling it out, then it's a hole and not an asymptote. So this one remains an asymptote. So what we're going to do, all of us, is we're going to go to where x equals 1, and we're going to make a nice light vertical line through x equals 1 like this. Understand, and a lot of people make those dotted. I don't necessarily know that I need to do that, but it's pretty common for people to make their asymptotes dotted. I don't really, quite frankly, care. Good idea, though, to make them in a different color. We also should find a horizontal asymptotes moving forward, probably not tomorrow. It's probably a next week thing. We're going to start seeing problems that don't have horizontal asymptotes, but I'm going to keep you today where they all do. And so we should find it because if it's there, it provides skeletal structure for like the graphy flesh to hold on to. And so a vertical asymptote is rad, but a horizontal asymptote is double rad. Now, you might ask yourself, where am I supposed to find a horizontal asymptote? And the answer in this particular case is loaded. Again, encroaching on almost a calculus-y idea. Picture the biggest number you can think of. You got it? Imagine the largest number in the known universe. Now put it in place of x. What does that fraction get really close to if your number goes in place of x? Thank you. That's called a limit. What's happening there is if x, you might say, oh, I'm thinking of a really big number like 500. No. Don't be a goofball. I'm talking like trillions. I'm talking like quadrillions. If x goes into the stratosphere to the point where it's the biggest number ever heard of, and you put it in place of x, 4 divided by that, that's pretty dang close to 0, right? So generally, a rational function has a horizontal asymptote at 0 if you can say that about it. If I put in big X and I get 0, there's a horizontal asymptote. However, there is a vertical shift at the end of this function of -1. Where does the graph move to? Down 1. Therefore, there is a horizontal asymptote right there at down 1. As always is the case with this job that I do, these things take time. These things will take days for us to just practice and talk to each other and ask questions. But any rational function that looks like this is going to have a horizontal asymptote at 0. The only way we're going to move that asymptote up or down is if there's a vertical shifter at the end. That'll move it up or down. We have now skeletal structure, and now it's time to get in there and try to make the graph. You should already know, based on the first part of the lesson, just pretty generally what this graph is going to look like, right? We know it's going to be some sort of curve that's going to exist up here and down here, but that's we can do better than that. And this really is where now we go from relying on just generally what we know to let's get in there and get dirty. Let's go find some points. So this is where we want to go off to the side. You don't have to make a formal table if you don't want to. It's okay. But like, I'm curious to know what happens if I put 2 in place of x. You should be too. Because every time I can give it an input and it gives me an output, that's one more dot for my game of connect the dots. And at this level in your math career, I shouldn't have to show work on something like this. So I'll talk you through it. What's 2 minus 1? 1. What's 4 divided by 1? And what's 4 minus 1? So we just discovered that the point 2, 3 can be marked as a point on the curve. In order to avoid fractions, I personally think that the next x that we should choose is 5. What happens if you put 5 in the bottom? What's 5 minus 1? What's 4 divided by 4? And what's 1 minus 1? Good. So we can now say that there's a point at 5, 0. I don't feel like that's enough. I won't sleep well tonight if we were to leave it like that. I'd like a little bit more information in between those dots. So as annoying as it is, calculator, no calculator, whatever, let's get a little bit more specificity in the 3 and 4 area. So let's try 3. This one won't be bad at all. What's 3 minus 1? 2. What's 4 divided by 2? What's 2 minus 1? Boy, we're on a roll here. And the other one that's in between there is 4. I'm curious about 4. So if I input 4, and again, I would worry about this in a 9th grade class, not here. If you put in 4, what's 4 minus 1? 3. What's 4 divided by 3? 4 thirds, or 1 and 1/3. And what's 1 and 1/3 minus 1 whole? 1/3, 0.3, if you, whatever you want to call it. And now we can put a little bit more of a specific twist on those dots. I can get a little bit more stuff to hold on to. The more points you give my graph to hold on to, the better off it's going to be. So I'm going to go to 3, 1. And I'm going to go to 4 and 1/3, which I'll approximate to be right about there. And there you can now make out the shape, the asymptotic sort of behavior starting to form. And at that point, you're green lighted to make the curve. So the way you make these curves is, your curve's going to approach this vertical asymptote asymptotically up here. So you can kind of start with that side. And then of course, it's going to be that plane coming in for a landing over here. And then as always, the challenging part, good luck, my friends, is trying to make it curve and not look like a crackhead did it. It's not the easiest task. I know we sometimes joke about it, but you got to make a decent looking curve. I'm just going for it. Look at me. I'm just going to write it. Hold on a second. Look at that. Did I just do? Look at that. That's what. Anyways, but we're halfway home. Did I what?
I said we do joke about crack. It's all.
Should do that, should I? So now what we can do is we have options. Option one is you can reflect the curve to the other side. Option two, if you really struggle with visuals, is you could just go do all the math again. I choose option one because I think we can handle this. So it all becomes sort of a flippy floppy thing. So I think to myself like this. Okay, so I go back to this. This is like my new, look at the big green dot. That's like my new origin, right? So if you think about the point here, oh my God, that was about to be a disaster. You see that thing coming in? If you think about that point I just circled in red, would you agree that that point relative to the quote unquote origin is 1 unit off to the side and 4 units above? So I should be able to reflect it 1 unit to the side and 4 units below. So 1, 1, 2, 3, 4. So I don't really need to do the math to verify that the point 0, -5 is in there. Right? Pretty slick indeed. And so once you do all the math on one side, much like a parabola, you can just carefully, it probably takes a little more brain power with this one, but you can reflect all the points to the other half. Okay, and then you just keep going. So like from this one, I went 2 down closer to the asymptote and then 1 out. So I'm going to go 2 down closer to the asymptote, 1 out. And then for the next one, I went down to a third, 1 over. And then I went down to the line and 1 more over like this. So it's not cheating at all. It's just work smarter, not harder. We've already done all the math. Now we just make the graphs look symmetrically the same. Any questions about that? So here's what we didn't do. I got a little bit excited, so I didn't follow my own directions. So when it comes to doing these problems, I have to follow the directions. And it said to name all the holes, vertical asymptotes and horizontal asymptotes. So for this problem, I would just write holes, none. Remember, the holes are only going to come to exist later on. We probably won't get there today. The holes come into existence when there's a number X isn't allowed to be, but it crosses off with something in the top. Okay. And as far as vertical asymptotes, you can call them VAs. So vertical asymptote at, you can put a colon, you can put the at sign, whatever you want to do. What's the name of our vertical asymptote? Good job. Thank you for saying X equals. That's awesome stuff. Don't put vertical asymptote at 1, at X equals 1 is better. And then horizontal, that HA at where? Nice job, dude. So in every problem, later on, it'll get more complex when we have like slant asymptotes. But for today, we're just going with verticals, horizontals, and holes. So let's talk about a couple more, and then we'll get to something infinitely more entertaining than this. Just real quick, like number 4, pop quiz. Can you tell me where the vertical asymptote is on number 4?
Right, 3.
At X equals 3. Can you tell me where the horizontal asymptote is for number 4? Horizontal asymptotes are never X equals. What? Y equals -2. Very good. Are there any holes?
No.
No. The only way there would be a hole is if that X minus 3 in the bottom could be eliminated, canceled out with another X minus 3 on top. And since that doesn't exist, then there are no holes. Let's turn our papers over and go to the back. Number 5 is actually pretty dang boring, so let's skip that. Let's go straight to number 6. That pen is driving me crazy. I know that I'm not driving me crazy isn't like at the top of your list of things to do, but your incessant clicking is making me pretty much want to just crawl up in a little ball and cry like a baby. It's been happening for like 16 minutes and I've been really proud of myself because I've just been handling it, but I just couldn't do it anymore. So I had to say something. You're clicking, Lauren's clicking. It's just that it's just incessant. I was just taking it like a champ. There, I got it off my chest. What do you think we do in problem number 6? Starts with an F. Yeah, we got a factor, man. So let's see what happens. Let's see what becomes of this. This is a little bit of a mess of a rational function. The top is pretty much just what it is. And then the bottom is, let's test our skills. How could we factor the bottom?
You need a 2x and an x, right? One and three.
No, you're overlooking something massively important. The GCF, right? Remember, not pulling the GCF is really always going to make our lives a lot harder. So I do identify, as do you, that everything in the bottom can be divided by -2. So if I pull the -2 out, what does the bottom now look like? Good job. It's the oldest factoring trick in the book is just make your life easier. If someone gives you a GCF, take it because it's going to make what you actually have to factor a lot easier to see. And then you can now see the little double parenthesis factors that make up the long red thing. What are they? Nice job. So I wanted to make sure we got to this point, just because I didn't want you to walk out of here today and think that maybe these holes are, things of lore and legend. They exist. So going into a problem like this, the first thing that we would consider is always, what is X not allowed to be? What 4 or right. So if this were a yesterday problem, we would say the values that are excluded are 4 and 1. But what we need to talk about now is that they're excluded in different sorts of ways. We think about the 4. So X is not allowed to equal 4. And X is not allowed to equal 1. But the question is, which one of them can be removed? The 4. Because the X minus 4 on top can cancel or eliminate the X minus 4 on bottom. That is what we call, sorry for the big words here, you don't have to know it or write it down, but it's called a removable discontinuity. So any discontinuity that you see is going to be in the form of like an asymptote, or in this case, a hole. It's just a place where the graph can't be continuous. It can't continue over that point. So we have discontinuities at 4 and at 1. One of them is removable, specifically 4, because you cancel this out and you cancel this out. So we make a note right now that there is a hole at X equals 4. If I were to graph this on Desmos, Desmos does not even show the hole. I could zoom in for 20 minutes to its maximum zoom and I still can't see the hole. The hole is infinitely small. When we graph, as you'll see in a couple minutes, we go out of our way to make the hole visible. Like we want you to see it. So we put a little, like one of those little open circles like we use. We just stick one there. You'll see. What else do we know? Is there a vertical asymptote? X is also not allowed to equal 1. So there is a vertical asymptote at X equals 1. I realize we're far enough into the lesson that the professionals, the authors would say that I should stop talking because you're not physiologically capable of still listening, but I believe in you guys. I need you to hear this. When you're doing rational functions, if the degree of the top is less than the degree of the bottom, hear me? Then there's a horizontal asymptote at 0. The degree, do you guys remember the word degree? What is it? What's the degree of the top? 1. It's right here, because this right here is X to the power of 1. So we say that the degree on top is 1. What's the degree on the bottom? And since 1 is less than 2, there will be a horizontal asymptote at Y equals 0. And it doesn't have to go and change like it did in the last problem, because after the rational part, the fraction-y part, there's no happy little plus or minus. So the horizontal asymptote's just going to stay right at 0. This is something I struggled with when I was 17, learning this. And it's the following question. Imagine the biggest number you can think of. Again, I'm going to be asking you this a lot over the course of the next half year or year and a half if I see you again. The biggest number in the universe. Put it in place of X. What does that fraction equal? What does it get close to?
0.
Does. And I had the hardest time with that when I was your age because I'm like, I just cry foul because I feel like if I put a trillion in the top, doesn't that mean something? It doesn't relative to the bottom. Because if you put a trillion in the bottom, you have to do a trillion squared times -2. And what happens is over time, the limit of this says, I don't care how big you go, eventually this thing is going to tend to 0. And that's why the horizontal asymptote is at 0. Okay. So look, we followed directions. We have a hole at 4, we have a vertical asymptote at 1, and we have a horizontal asymptote at 0. Let's graph our asymptotes. You bet your asymptote. Let's get it done. So we're going to graph a vertical asymptote at 1. And we're going to graph a horizontal asymptote at 0. There you go. Now we have the skeletal structure, the bones on which the flesh can hang, and now it's time to make a graph. We've never seen one quite like this before, so we probably don't want to make any assumptions about what it's going to look like.
So since we have like
Put that anywhere.
the X minus 4 is canceled,
Yeah,
could we simplify?
you can use the simplified version or you can use the unsimplified version. That's a good question. I think the question you're asking is, can I consider the function or can I consider or think of the function as 1 over -2 times X minus 1? The answer is sure. So now we have to just get in there and get our hands dirty. And really, it doesn't take a lot. What I really want to know is to the right and the left of the vertical asymptote. If I can just get a little information, I can usually logically construct the graph from there. So what's the number closest to the right of the vertical asymptote? It's right there. It's 2. So I really want to know what happens if I put in a 2. A lot of probably intense calculations here that you might want to keep, lots of scratch paper handy, but I'm going to walk you through it. So okay. So if we put 2 into this function on top, we don't get anything. We just get 1 over. So again, you can go back and use this one, but this will make our lives a little easier. If we put 2 down here, what's 2 minus 1? And what is -2 times 1? So we get 1 over -2, aka -1/2. Got it? So if you wanted to right now, you could go graph a point. You can wait and like stockpile your points and use them later. It's up to you. But I'm going to go right from the old origin. Remember or not, don't go from the intersection of your asymptotes. It's not a real origin. We're going to go back from 0, 0. We're going to go to the right 2. We're going to go down 1/2, and we're going to be right where that dot is. I need to get rid of that eraser or that arrow. So we just learned something interesting. We learned that we got at least 1 quadrant flipper. Okay, let's see what happens if we put in like 3. What happens if you put in 3? 3 minus 1 is 2, -2 times 2, -4, you get a -1/4. And so we see that the graph is behaving as we would hope that it would. Right? So I think we have enough information at this point in time to get in there and make a sketch. If you wanted to, you could find a y value for the x's between 1 and 2. I don't really think that that's necessary. We can see the behavior of it. We know it's going to go asymptotic over here. And then it's going to be a pretty tight curve in here like this. And then it's going to back off, not back off, but like it almost comes up and it's like it's trying to make sweet love into that asymptote, but it just can't quite get there, right? You know what I'm saying?
Yes.
Yeah, maybe not the best way to say that, but that's never stopped me before. Let's go left of the asymptote. What's the first number to the left of the vertical asymptote? Oh boy. She said 2. Good. So let's do 0. 0 is the horizontal location first that we encounter to the left. If we put in a 0, what is 0 minus 1? What's -2 times -1? And what's 1 over 2? Well, it's 1/2. And so we can already kind of see, like, again, we could have just reflected these quite frankly, but I want to know more about, because there will be graphs that don't behave as expected, just FYI. So we're going to go to 0. We're going to go to 1/2. That's enough information right there for me to see that the next arm of the graph, that's what we call those arms, is going to occur up in the second quadrant. So from here, you can do more points if you want to, or you can just say, I got it. I know how it's going to behave. It's going to asymptotically hug onto that horizontal. And then in here, it's going to, again, take a tight curve like that. Got it? I want to say one more thing before you start shuffling around and packing up. If you take a look at, and I do want you to hear this and absorb this because I meant to get to this. Take a look at number 7. Do you see how the degrees on the top and the bottom are the same? I'm going to say something and I want you to see if you can tell me why. Because the degrees are the same, I can tell you that that graph has a horizontal asymptote at y equals 1/3. The heck? Why would I say that? Where's that coming from?
Degrees. It's 1/2².
Exactly. So like if you were right now on number 7 to vandalize it and put a little 1 in front of the x squared on top, what you're going to do is when the degrees on the top and the bottom match, you're going to get a horizontal asymptote at the ratio of their coefficients. So like if the top said 2x² and the bottom said just regular x², then there'd be a horizontal at 2/1 or 2. So what we learned today is that if the degree on top is smaller than the degree on bottom, where's our horizontal? 0. But if the degrees match, where's our horizontal? At the ratio. And then next time, well, probably not tomorrow, we'll talk about what happens when the ratio or the degree on top is bigger than the degree on bottom. That's when things start to fall apart a little bit. But I think we made a lot of progress today. You know a lot more about rational functions than you did 45 minutes ago. That's good news. Don't lose this. Hold on to it. Don't feel like you need to get it done unless you really want to. We'll work on them some more tomorrow. I didn't mean for it to be that kind of day, but it turned into just a lot of talky. So don't forget all that.
I'm gonna give out Monday and Monday. I'll check.
Okay. Would you guys be interested in yelling hello to Blair into the microphone, or is that really dorky? Would you do it like on a 1, 2, 3, like say bye, Blair? You guys interested?
Yes.
Got to be really loud. Really loud. Are you ready? Okay, 1, 2, 3. Wow, you guys are great. Thank you. Okay, bye, Blair.
Anyway,